So I'm going to go through several examples of chain rule that involve our trigonometric functions and exponentials, logarithmic functions, and you'll see other rules that are applied within as well. So this will be a good practice or set of problems that illustrate the need to apply multiple derivative rules within the same equation. So let's begin. We have sine of 3x plus 1. I want you to recognize that sine has been composed with that linear function 3x plus 1. So when I see a function composition, we know that chain rule needs to be applied when calculating the derivative. So the derivative of y is dy dx. Chain rule, derivative of the outer function, still composed with the inner function, times the derivative of the inner function. So think we are scaling our derivative by the rate of change of the inside. So derivative of 3x plus 1 is just 3. And we could reformat this so it is 3 cosine of 3x plus 1 if you prefer that look. So that is the first one. Now we have sine over 1 plus cosine x all squared. So this is also a composition. Think that if we had a function x squared and we took this inner part and substituted it in for x, we would get the equation that we are currently looking at. So we recognize there's a composition, so we must do the derivative of the outer function, still composed with that inner function. So derivative of y, we can write as y prime as an alternate notation. Power rule, because we have a power function as the outer function, so we bring that 2 to the front. Keep it composed with the inner function. Subtract 1 from our exponent, so that is derivative of the outer composed with the inner. Then times the derivative of the inner. We see that the derivative of the inner is a quotient, so let's use quotient rule. Quotient rule, I'm going to section this off. When you go to do the derivative of the inner function, treat it like it's its own new problem. So look at it with a set of fresh eyes, fresh mind. You're doing this as its own problem, and be ready for using multiple rules again if necessary. So quotient rule, low, d high, minus high, d low. So the derivative of 1 is 0, derivative of cosine is negative sine. Over, low squared. Now let's clean up our derivative of the inner function first. So we're going to distribute that cosine to the 1 plus cosine x. So we're going to get cosine x plus cosine squared x minus, or plus, sorry, sine squared x. All over 1 plus cosine x squared. Trig identity, cosine squared plus sine squared is 1. So we actually have cosine x plus 1 over 1 plus cosine x all squared. We can see we can make a cancellation with that value in the numerator and 1 in the denominator. So this all simplifies or boils down to the following. Okay, so now we have that times, so our derivative, let's carry all this down, 2 sine x over 1 plus cosine x times 1 over 1 plus cosine x. I can multiply these denominators together if I want and put everything up top, so we could have 2 sine x over 1 plus cosine x all squared, if I want to clean all that up. And there is our derivative fully simplified and put together. Next we have a secant function composed with tangent. So again, composition, chain rule, derivative of the outer. So derivative of secant is secant x tan x. But instead of x, make sure it's still composed with tangent. Times the derivative of the inner. Derivative of tangent x is secant squared x. And there we go. There's your derivative. Next, we have a power function on the outside as our outer function. And then on the inner function, we have a linear term and then a square root of x. So we do have composition here. So let's apply chain rule. So we're going to say y prime is equal to, we're going to use that power rule and keep the inner function still composed within it. Then we have to multiply by the derivative of what's inside. So let's section this off. Derivative of x is just 1. Now how do we take the derivative of square root of x? Well, we mentioned that we can reformat radical functions as power functions. So I can rewrite it like this and then just use power rule. So if this is my general function, we can say, well, y prime must be 1/2 x to the negative 1/2 using that power rule. So that's what we're going to write in there. Now let's see what we can do in terms of cleaning this thing up. So that negative exponent, we can bring that to the bottom and just cube it. And what we have over here is we have times, and then it's going to be 1 plus, this whole thing is going to be 1 over 2 root x. If I want to combine what's inside that parenthesis by adding, we would need common denominators. So it would be 2 root x plus 1 over 2 root x. I'm not sure this does anything for us. It doesn't look like it really does. So we'll just leave our answer like the following. So I'll erase this bottom piece because it proved to be a useless effort. So there's your derivative. Next, we have y equals cosecant x plus cotangent x to the negative 1. So hopefully by now we're recognizing our outer function's a power function here, and we're composed with cosecant x plus cotangent x. So when we take our derivative, let's utilize that power rule and keep it composed with that given inner function. We have to multiply by what's on the inside. So derivative of cosecant x is negative cosecant x, cotangent x. And then the derivative of cotangent is negative cosecant squared x. All right, so let's see if we can do anything with this. Well, let's move this down to the denominator. So we have the following. All squared. Then we can take out a negative cosecant x. So let's do that. And we'll have cotangent x plus cosecant x, which is nice because that will cancel with that thing in the bottom there. So we're going to multiply this piece here by negative 1, move that to the numerator. So we're going to have cosecant x, cotangent x plus cosecant x. And then this is all over cosecant x plus cotangent x squared. So we get that cancellation here with one of these. So now we're at cosecant over cosecant x plus cotangent x. And there is your derivative. So that one worked out nicely. Next, we mentioned in class, whenever we see exponents with these trig functions, let's reformat so we can have a better understanding of what's actually happening when we're going to calculate the derivative. So the following format is equivalent to what we originally have. And the reason why I like to reformat this is because now I can see a composition really clearly. And whenever I have composition, we know chain rules going on. So let's do each piece. We have power function as the outer, still composed with the inner, times derivative of the inner. So that's our first one. And then we're going to have minus okay, same idea on that second piece. Let's clean this up. write negative 5 cosine x up top. And then plus, and when we multiply this out, that's going to stay up top, so we're going to have 3 cosine squared x sine x. And that looks like the best we can do. Next, we have a product of two functions here. So we need to recognize that it's x cubed times this function. And whenever we have a product, we need to use product rule. So let's establish that first. When we go to do the derivative, product rule, left, d right. Now, the thing is, when we take the derivative of this right function, that is a composition. So we must use chain rule on that when we're calculating that derivative within the product rule. So let's do that. So we're going to bring that to the front because we have a power function as the outer, then times derivative of the inner, which is 2. Plus right, d left. All right, let's clean this thing up. So 4 and 2 is 8. We'll bring that even all the way out to the front. Plus, and then we'll have 3x squared, 2x minus 5 to the fourth. And we will leave it like that. The big thing from this problem I want you to take note of is recognizing there's a product initially, so it calls for product rule. And within the product rule, when we had to take a derivative of one of our pieces, that required a chain rule to calculate. So there's an example of a chain rule within another rule. Now we're on to another product here. This times this, so we have a product rule to use. We see that there's an exponent with our trig function, so before we start the product rule, let's reformat. Again, this helps me visually see I have composition. There's also a composition with that tangent piece that we'll get to. But let's use product rule now. So left, d right. Now when we take the derivative of tangent 4x, 4x is composed within the tangent function, so we got to use chain rule. So derivative of the outer, which is secant squared, still composed with the inner, times the derivative of the inner. Plus right, d left. Derivative of our left function. We see that sine has been composed within a cubic function. So power rule for the outside, still composed with the inside. Subtract 1 times the derivative of the inside. Let's see if we can clean this up a little bit. Bring the 4 out front. And I think we'll leave it there. So there you have an example of two chain rules within a product rule. All right, next. We got this radical function that has a composition within it. So before I even start, it's always wise to reformat radical functions like power functions. There we go. Now I see the composition within that original square root, so I know chain rules needed. I've just converted this over to a power function so I can use power rule. So bring it to the front, keep it composed with what's inside, subtract 1 times the derivative of what's inside. Now we're going to have multiple pieces, so we'll section this off. Derivative of secant is secant x tan x, plus the derivative of tangent is secant squared x. And again, the individual secant x and tan x, it's just composed with x. The derivative of x is 1, so if you want to mistakenly use chain, well, if you, not mistakenly, but if you accidentally use chain rule, which isn't the worst thing because you're just going to be multiplying by 1 because the derivative of the inside is 1. But when it's just composed with x, chain rule is just additional work that's not needed. So there is what we have. Let's see if I move that down below. This piece on the left with the negative exponent, I could have the following. 1/2 is square root, so I could repurpose that so that it looks like this. And then up top we have times so to me that looks like the best that we're going to get. So we'll leave the derivative like that. Actually, on second thought, we can do a little more with this. So let's backtrack here. We're going to keep that thing up top. But I should recognize we can take a secant out of what's over here. Now, through multiplication, we can move that secant to the front. And what we have now is the negative 1/2 times tan x. And tan x plus secant x is the same thing as secant x plus tan x. So I can just rearrange the order so that becomes now more visible, where I have two things with the same base being multiplied together. So I can put them into one by adding their exponents. So it becomes a positive 1/2. And then we have 2 secant x plus tan x. So again, adding exponents. So back to like basic exponent rules. If you have x squared times x third, you just add the exponents. Good thing I can add. So same idea here. It's just instead of x, we have secant x plus tan x. So I can combine it to 1, and now it's a positive 1/2. And if I really want to, I could write it back as a radical. And that's the fully simplified answer. So is it necessary to take all those steps? Probably not. You probably could have just stopped there, because that shows that you just know, or even a step above that, sorry. So getting to there shows that you know the derivative rules and how to apply them. Simplifying it all the way is a little intense. I didn't recognize it at first, but after observing the answer and seeing that through, you can reach that point in the way I just showed. All right, now back to this idea where trig function, exponent is repurpose or reformat, not repurpose, poor choice of words. So that looks like this. So now I can clearly see a composition within a basic quadratic, say x squared. That sine of 3x minus 2 has been composed within it. So I can see a chain rule is needed. So power rule on the outside, keep it composed. Subtract 1 becomes 1. Now we're going to multiply by the derivative of the inside. Now the inner function has a composition itself. So I'm going to have to use chain rule again. So this is what I mean by when you go to multiply by the derivative of what's inside, you're going to treat it like it's its own new problem. So derivative sine of 3x minus 2. We're going to do the outside, still composed with the inside, times derivative of the inside. So a multi-layered chain rule application. Clean it up. And there's your answer. Next, we got to find the second derivative of this problem. So first derivative, just knowing your tangent derivative, which is secant squared x. So now we got to find the second derivative. Trig function with an exponent reformat. How we can see the composition. So power function on the outside. Subtract 1 times derivative of the inside, which is secant x tan x. So cleaning that up, 2 secant squared x tan x. And there's your second derivative. So get used to getting the habit of reformatting trig functions with exponents so that you can see the composition. All right, now we got a table of these values, so I'll make that a little more clear. We're just going to do a through d. So we have to find the derivative of that given expression and evaluate it at that x value. So for a, derivative of 5f of x is going to be 5f prime of x. And the reason we're doing this, we want to get used to writing derivatives with function notation, minus g prime of x. And we want to evaluate this when x is equal to 1. So f prime of 1, we use the table, it's negative 1/3. So we can make that substitution. G prime of 1 is negative 8/3. So we have negative 5/3 plus 8/3, which is 3/3, which is equal to 1. So that's A. Let's look at B. So B, we have product of f times g to the third, so we can reformat that if you want. So instead of this to the third, you could write it like this so you can see the composition. That's a product, so we're going to have to use product rule. So we're going to do left. Now D right, we see the composition. So outer, which is power function, still composed with the inner, times the derivative of the inner, plus right, D left. We want when this is all calculated when x is equal to 0. We're going to use the table to figure out what they all are at 0. So f of 0 is 1. And we have 3 times g of 0 is 1 squared. G prime of 0 is 1/3. G of 0 is 1 cubed. F prime of 0 is 5. So let's clean this up. We're going to have 3 times 1/3, which is 1. So this whole thing here is just 1. And then plus 5, which is 6. So that is B. Lastly, D. We have a composition there. G is within F, so chain rule. So derivative of the outer, still composed with the inner, times derivative of the inner. And we want it when x is equal to 0. So G of 0 is 1. So we're going to get f prime of 1 times G prime of 0 is 1/3. So now we got to do f prime of 1, which is negative 1/3. And we get negative 1/9. So when you have composition for function evaluation, again, make sure you do, or not again, but make sure you do the inner first, and then figure out what that is, and then evaluate the next piece. So for instance, g of 0, we found out was 1, so then in line 2, now we do f prime of 1, and that's how we get to the negative 1/3. And there's your final answer. I'll leave the other parts to you, but there are the first A through D. Now we're on to exponentials and logs. So we have 2 times e to the x. Constant multiple rule, I can just leave that 2 and then take the derivative of e to the x and multiply it by that constant in front. Derivative of e to the x is itself, and there's your answer. Next, exponential functions. So these aren't power functions. So remember, power functions have a base of a variable. Exponentials have base of a number. Okay? So I can't use power rule here. However, when I see a function in the exponent that's not just x, I know some sort of composition is going on. So we have chain rule that needs to be applied here. So we do outer. The outer is the exponential itself, still composed with the inner, times the derivative of the inner. So the inner function, again, is that function that appears in the exponent, which is negative 5. So final result, so remember, power functions, base equals variable. Exponential, base equals number. And with power functions, we can use power rule. For here, cannot use power rule. They have their own set of rules that I gave to you in class. So don't confuse those two. Make sure you're using the right rule for each one. Over to here, we have a product of two functions here and also a product of two functions there. And then the difference between them. So for each individual piece, we're going to have to use product rule. So let's do left d right, which is itself, plus right d left. So that is just handling that piece, and then it's minus, and I'm going to use product rule on that second piece. So left d right plus right d left. We can distribute that negative. Let's see if we can get anything. So I'm going to factor out an e to the x from that first piece. Factor out an e to the x again. Actually, every term is going to have an e to the x, so let's take a step back here. Let's take a few steps back. Let's distribute that negative. So we get this. Every term has an e to the x, so let's take that out. And what are we left with? X squared plus 2x minus x minus 1. We can combine like terms there. And we'll use that as our final derivative answer. So in this problem, two separate product rules that need to be taken into account. Again, recognizing when a product between two functions occurs, make sure you use the product rule. Don't just do the derivative of the first times the derivative of the second. All right, so now we have an exponential that is not base e. So in general, recall that when we have a function that is not base e, its derivative is a copy of itself scaled by the natural log of that base, which is why when we do base e, that's just a special case. Natural log of e is just 1, which is why we just have e to the x there, following that general formula. So let's carry that over into this example. Derivative exponential is itself scaled by the natural log of the base. And there you go, done. There's no composition outside of just the variable x, so I don't need to use chain rule. Next, we have an exponential. This time we do have a composition with a negative x. So let's take that into account. So when we take the derivative exponential, you copy it over. It's itself scaled by the natural log of the base. So that was the derivative of the outer times the derivative of the inner, which is negative 1. So derivative of the outer first times derivative of the inner. We can clean that up if we want. And we'll leave our answer like that. Same idea again. Exponential, we should see the composition. We have a function inside that exponent. So we know we have to use chain rule. Derivative exponential is a copy of itself, still composed with the inner, scaled by the natural log of the base, times the derivative of the inner function. Derivative cotangent is negative cosecant squared x. You can move that negative in the front if you want, but other than that, that's about as good as you're going to do. Natural log functions, or logarithms in general. So logarithms of any base. When you calculate the derivative, it's going to be 1 over what you're taking the log of times the natural log of the base. Okay? I mentioned in class that you could restructure or change a base formula if you're more comfortable dealing with natural logs. And the reason you can do that is because when you repurpose it, or restructure the equation in this new format, 1 over ln a is just a constant. So you can just leave that out front when you calculate the derivative of whatever this piece is. Because most people find calculating the derivative of just a natural log function much easier than when you have a logarithm of a different base. So that's an option. Here we do have a natural log, so I don't need to do change of base if that's what I ultimately prefer. But when we do natural log derivatives, in general, it's 1 over x. But here we have a composition of x squared within our natural log, so it's going to be 1 over, still composed with that inner function. So we keep the composition, and then we multiply by the derivative of the inner function, which is 2x. So and there's your final answer. Okay? So it's 1 over, and then keep the composition, and then multiply by the derivative of that inner function. Here, we have natural log as the composed function within our quadratic piece x squared. So this is pretty similar in terms of notation, but off enough to change the problem completely. Power function on the outside, keep it composed with ln x, subtract 1, so it goes to 1, multiply by the derivative of the inside. So we get 2 ln x over x. So much different than the previous problem, although and all it took was a change in the location of the parentheses. Here, you should see we have a product of two functions here, so that's going to require product rule. So we're going to do that, and then we'll do that minus x off at the end. So left, d right, minus right, or sorry, plus right, d left. So derivative of x just 1. So there's your product rule, and then derivative of negative x is minus 1. So then we have x times 1 over x is just 1 plus ln x minus 1. 1 minus 1 is 0. So ln x is the derivative of x ln x minus x. Logarithm that is not base e. So I'll do this in two ways so you can see how to use that change of base if you prefer that way. So the derivative, when we have logarithms of different bases, it's going to be 1 over. And again, normally it's just 1 over x, but we have a composition, so you want to keep that composition scaled by the natural log of the base of the logarithm. But because we have a composition, we got to use chain rule, so I have to make sure I'm multiplying by the derivative of that inner piece. The inner function is x squared, so times 2x. We can simplify this. And there's your final result. If you wanted to take an alternative approach, because you prefer natural logs and you forget that logarithm of a different base other than e, we can change a base into the following. Again, this piece here is just a constant. So now we can use constant multiple rule and leave that constant in front while I calculate the derivative of ln x squared. So ln x squared, there's a composition. X squared is within our natural log. So we again have a chain rule that's needed to be applied. So we're going to do 1 over, keep the composition, times the derivative of what's inside. So we have 1 over natural log of 4 times 2x over x squared, which simplifies to 2 over x. We're going to get 2 over x ln 4. You can see that we get the same result. So again, it's really a matter of preference. You can do the change of base and just deal with natural logs if you ever get presented a logarithm that is not base e, if that is what you like. If not, if you can understand and remember the formula for logarithms of any base. And remember, even natural log is just a special case of that situation. So if you know that log of any base formula, feel free to use that as well. I'll do both ways again because we have a logarithm of base 2. So calculating the derivative, you should see composition. So we're going to have to use chain rule here. It's going to be 1 over. Keep it composed. Scaled by the natural log of the base of the logarithm. Okay, times, well, what's the derivative of what's inside? Okay, so 1 over x. Here's what you can do. 1 over x. I don't want to do quotient rule, even though it's a quotient. It's a lot of work. It's unnecessary because I can reformat so it looks like this. Now I have a power function, which is much easier to use power rule because when I calculate the derivative of that inside, bring it to the front, subtract 1. Let's clean this up. So we have 1 over. We're going to call 1 over x, x to the negative 1, ln 2 times negative 1 over x squared. We're then going to bring that x to the negative 1 to the numerator. So we have this. We'll get a cancellation here. And we will ultimately have negative 1 over x ln 2. Let's also try with the change of base method. So we can do y equals natural log of what you're taking the log of over the natural log of the base of the log of. You can separate so that you can see that 1 over ln 2 is just a constant multiple. And therefore, we can leave it alone as we calculate the derivative of ln of 1 over x. So ln derivatives, it's 1 over, where you're trying to take the derivative of, 1 over, and then keep it composed with what's inside, times the derivative of what's inside. We already calculated that. Up above, it's going to be negative 1 x to the negative 2. And again, how do we do that? We changed that rational function into a power function. That was an option there. That way I didn't have to use quotient rule. Let's clean up the math here. Dividing by 1 over x is the same thing as multiplying by the reciprocal, which is just x. So we're going to have times x times negative 1 over x squared. You'll see we get that cancellation again, and we get the same exact answer as before. So change of base proving to be valid once again. And that is the conclusion to a bunch of chain rule examples that have exponentials, logarithms, trig functions, power rule, quotient rule, all embedded within each other. And we will practice more as class progresses, but that is where I will end this video.